New unit, new subject. We're talking about water today. That's what the ocean is made of, so it's very important. Water is a polar molecule, meaning that there's not an even distribution of the electrons across the molecule. Oxygen tends to hold the electrons much more than the hydrogen does, which makes the hydrogen have a partial positive charge and the oxygen has a partial negative charge. Positive charges on one molecule and negative charges on another molecule attract each other, and they form hydrogen bonds. Due to water's polarity, water molecules stick to each other, and they form hydrogen bonds. Hydrogen bonds are not very strong. They're very weak. Cohesion refers to the attraction of molecules for other molecules of the same kind. And water molecules have strong cohesive forces, thanks to their ability to form hydrogen bonds with one another. Due to polarity, water sticks to other surfaces. Adhesion. Adhesion allows water to stick to unlike surfaces, such as in a graduated cylinder, water makes a meniscus because it's sticking to the sides of the glass. Due to polarity, hydrogen bonds form at the surface of the water, forming an elastic film. Things that are light enough to, like water bugs, can live and exist in the ecosystem on the top of the water. Unlike most substances, water becomes less dense when it freezes. Hydrogen bonds first condense when water is cold, but then expand when water freezes, leaving air pockets between the water molecules. Ice floats as an insulator to water in a body so that fish don't die in the winter. Because of water's polarity, it's a universal solvent, which means it can dissolve many things. The solute is the material that is being dissolved in a solution. Water cannot dissolve polar molecules. Water cannot cut. Because of water's polarity, it is the universal solvent. It can dissolve many things. The solute is the material being dissolved in a solution. Water cannot dissolve non-polar. High specific heat. Hydrogen bonds give water all of its properties. Remember that. That's very important, including an abnormally high specific heat. This means that water resists changes in temperature. Large bodies of water, such as oceans and lakes, can absorb large amounts of heat with only small changes in temperature. This protects organisms living within the land around it. This is one of the causes of wind and breezes. Solutions are either acidic, below 7, base, above 7, or neutral, 7. When carbon dioxide dissolves in seawater, the water becomes more acidic, and the ocean's pH, a measure of how acidic or basic the ocean is, drops. Even though the ocean is immense, enough carbon dioxide can have a major impact. In the past 200 years alone, Ocean water has become 30% more acidic, faster than any known change in ocean chemistry in the last 50 million years. By about 4 billion years ago, the first permanent accumulations of water were present on Earth, forming oceans and other bodies of water. Water moves between these different reservoirs through a hydrologic cycle. Water is evaporated from the oceans, lakes, streams, and surface of the land, and plants transpiration. By solar energy, all of this moves. It is moved through the atmosphere by winds and condenses to form clouds of water droplets or ice crystals. It comes back down as rain or snow and then flows through the streams, rivers, into lakes, and eventually back into the ocean. Water on the surface and in streams and lakes infiltrates the ground and becomes groundwater. Groundwater slowly moves through rocks and surface materials. Some of it will return to other streams and lakes, and some goes directly back into the ocean. Water is stored in various reservoirs as it moves through this cycle. The largest, by far, is the oceans, accounting for 97% of the volume. Of course, that water is salty. The remaining 3% is fresh water. Two-thirds of our fresh water is stored in the ground, and 1/3 is stored in ice. The remaining fresh water, about 0.03% of the total, is stored in lakes, streams, vegetation, and the atmosphere. To put that in perspective, let's think about putting all of Earth's water into a 1-liter jug. We start by filling the jug almost full with 970 milliliters of water and 34 grams of salt. Then we add 1 regular size ice cube, representing glacial ice, and 2 teaspoons, less than 10 milliliters, of groundwater. All of the water that we can see around us in lakes and streams and up in the sky can be represented by adding 3 more drops from an eyedropper. Most of the salts and dissolved elements in the ocean were probably outgassed along with water vapor, so the ocean has probably always been about as salty as it is now. But we know that rainfall and other processes weather rocks on the Earth's surface, and runoff carries dissolved substances into the ocean, contributing to its salinity. Yet despite this constant input, the ocean salt composition remains essentially the same. Therefore, the rate of input of new materials must be balanced by the rate of removal. In other words, the ocean is in a steady state regards to salinity. So what about lakes? They're subject to runoff and river input. Why are they not salty like the oceans? One reason is that compared to the ocean, lakes and ponds are relatively temporary phenomena. They do not last long enough to accumulate the same level of ions as the ocean. It should be noted that there are some lakes that contain water whose salt content may rival or exceed that of the ocean. These lakes usually lack river outflow. The Great Salt Lake in western United States is an example. All of the salts and ions that dissolve in seawater contribute to its overall salinity. Salinity of the seawater is usually expressed as in grams of salt per kilogram, 1,000 grams of seawater. On average, about 35 grams of salt is present in each 1 kilogram of seawater. So we say that the average salinity of the ocean is 35 parts per thousand, ppt. Note that 35 ppt, parts per thousand, is equivalent to 3.5% parts per hundred. Many different substances are dissolved in the ocean, but 6 ions comprise about 99.4% of all of the ions in seawater. These 6 major ions are chloride, sodium, sulfate, magnesium, calcium, and potassium. Chloride and sodium, the components of table salt, sodium chloride, make up over 85% of the ions in the ocean. This is why seawater tastes salty. Because of the six major ions in seawater compose over 99% of the total salinity, changes in abundance of the minor constituents have little effect on overall salinity. But given the vast size of the ocean, even minerals found in trace abundance can represent fairly large reservoirs. For example, gold is a trace element in seawater, found in concentration of parts per trillion. Yet if you could extract all of the gold in just 1 kilogram cubed of seawater, it would be worth about 20 million. Furthermore, the rule of constant proportion states that even though the absolute salinity of ocean water might differ in different places, the relative proportion of the six major ions within the water are always constant. For example, no matter what the total salinity of seawater sample is, 55% of the total salinity will be due to chloride, 30% will be due to sodium, and so on. Since the proportion of these major ions does not change, we call them conservative ions. Total salinity in the open ocean averages 33 to 37 parts per thousand, but it can vary significantly in different locations. But since the major ion proportions are constant, the regional salinity differences must be due more to water input and removal rather than to the addition or removal of ions. Freshwater input comes through processes like precipitation, runoff from land, ice melting. Freshwater removal primarily comes from evaporation and freezing. When seawater freezes, the resulting ice is mostly freshwater and the salts are excluded, making the remaining water even saltier. So differences in rates of precipitation, evaporation, river discharge, and ice formation play a significant role in regional salinity variations. For example, the Baltic Sea has very low surface salinity, around 10 parts per thousand, because it's mostly an enclosed water with lots of river input. Conversely, the Red Sea is very salty, around 40 parts per thousand, due to the lack of precipitation in the hot environment, which leads to high levels of evaporation. One of the saltiest large bodies of water on Earth is the Dead Sea, between Israel and Jordan. Salinity in the Dead Sea is about 330 parts per thousand, which is almost 10 times saltier than the ocean. This extremely high salinity is a result of the hot, arid conditions in the Middle East that lead to high rates of evaporation. In addition, in the 1950s, the flow from the Jordan River was diverted away from the Dead Sea, so there is no longer sufficient freshwater input. With no input and high evaporation, the water level in the Dead Sea is receding at a rate of about 1 meter per year. The high salinity makes the water very dense, which creates buoyant forces that allow people to float easily on the surface. But the high salinity also means that the water is too salty for most organisms, so only microbes are able to call it home, hence the name, the Dead Sea. But as salty as the Dead Sea may be, it's not the saltiest body of water on Earth. That distinction currently belongs to the Gayatol Pond in Ethiopia, with a salinity of 433 parts per thousand. That's right there. Very arid, very, very dry. While local conditions are important for determining salinity patterns in any single location, there are some global patterns that bear further investigation. Temperature is highest at the equator and lowest near the poles. So we would expect higher rates of evaporation and therefore higher salinity in the equatorial regions. Right in this area, right in there. This is a general case, but the figure below, salinity right along the equator, seems to be a little lower than at slightly higher latitudes. This is because the equatorial region also gets a high volume of rain on a regular basis, which dilutes the surface water along the equator. So the higher salinities are found at subtropical, warmer latitudes, with high evaporation rates and less precipitation, around the 30°. At the poles, there is little evaporation, which, coupled with ice and snow melting, produces a relatively low surface salinity. The image shows high salinity in the Mediterranean Sea. This is located in a warm region with high evaporation, and the sea is largely isolated from mixing with the rest of the North Atlantic water, leading to high salinity. Lower salinities, such as those around the Southeast Asia, are the result of precipitation and high volumes of river input. That would be right in here. In addition to geographical variation in salinity, there are also changes in salinity with depth. As we've seen, most differences in salinity are due to variations in evaporation, precipitation, runoff, and ice cover. All of these processes occur at the ocean's surface, not at depth. So the most pronounced differences in salinity should be found in the surface waters. Salinity in deeper water remains fairly uniform, as it is unaffected by these surface processes. Some representative salinity profiles are shown in the figure. At the surface, the top 200 meters or so show relatively uniform salinity in what is called the mixed layer, which is these here. Winds, wave, and surface currents stir up the surface water, causing a great deal of mixing in this layer and fairly uniform salinity conditions. Below the mixed layer is an area of rapid salinity change over a small area of depth. Right here. This zone of rapid change is called the Holocene transition zone. That is a very important word to remember, Holocene. Cut. In addition to geographical variation in salinity, there are also changes in salinity with depth. As we have seen, most differences in salinity are due to variations in evaporation, precipitation, runoff, and ice cover. All of these processes occur at the ocean's surface, not at depth. So the most pronounced differences in salinity should be found in surface waters. Salinity in deeper water remains relatively uniform, as it is unaffected by these surface processes. Some representative salinity profiles are shown in the figure. At the surface, the top 200 meters or so show relatively uniform salinity in what is called the mixed layer. The mixed layer. Waves, wind, and surface currents stir up the surface water, calling for a good deal of mixing in this layer and fairly uniform salinity conditions. Below the mixed layer is an area of rapid salinity change over a small change in depth. This zone of rapid change is called the halocline. Remember that this is important. Halocline. And it represents a transition between the mixed layer and the deep ocean, right in this area. Below the halocline, salinity may show little variation down to the seafloor, as this region is far removed from the surface processes that impact salinity. In the figure, note that the low surface salinity at high latitudes and high surface salinity at low latitudes is discussed above. Yet despite the surface differences, salinity at depth in both locations may be similar.